All right, good morning, everybody. Thanks for inviting me, Doug, to this awesome workshop. So let's get it started. I'm going to talk about music search and recommendation today. I'll try to keep it fairly high level this morning, just to kind of start too brutally at this time of the day. What I'm going to talk about is bringing the right music to the right people at the right time and place. Basically, the idea is the following here. As you probably all know, in the last 20, 30 years, things have changed a lot out there, from big studios and big CD stores to very small, crappy studios in people's garages to online uploading of music, and now tens of millions or hundreds of millions of songs being available anywhere online, as opposed to maybe a couple thousand songs being easily accessible in CD stores. So because of that big change, what you have is a setting where pretty much have accessibility to millions of songs that are accessed now by virtually anybody on the planet, right? And so on the other hand, there is all these very interesting devices that are out there to consume music, and so the big challenge is, how do we get the music that we're interested in from this very big pool onto our devices that, play this music? And so the idea really here is how can I find the music that I'm interested in without just ending up with, Justin Bieber or Britney Spears most of the time. And especially, how can I do that when I don't really have a good clue of artists or song names sometimes? Because there's a lot of people there that listen to some happy rock and roll, or they're bringing home their first successful date in a long time and they want some romantic jazz to play with saxophone or something. Or it's just October 31st and they want some scary Halloween music, right? So how can you find that type of music without knowing artist names or song titles? One way to go is, building computer algorithms that can automatically listen to these millions of songs that are out there and automatically tag them with meaningful words or meaningful descriptors, i.e. index the music that's out there and use it to build a search engine. Basically, the idea here is to index music with all kind of tags, like including genre tags, but not just genres, also things like, maybe should we try to figure a way to...
Can we turn off the... Is it going to leave us in the dark?
Like this? So we're going to tag music with tags as varied as mood as well, instruments, usage even, like, you can be used in the gym, used for a date and stuff like that. And so the idea really here is, can I build an algorithm that I feed the music waveform? And this is really what I'm particularly interested here, because there's many different ways that you could think about associating all these types of tags to music, but what we're really interested in is, can we just feed the waveform to the computer and have the computer listen to the music and then automatically tag it with appropriate tag, like for example jazz, romantic, piano, and good for a date in this case here. And then, basically do that for any song that you have in any large database, either a personal collection or music that's out there, for example, on MySpace. And then once you do that, now you have an indexed database of annotated music. You can then use that to deal with queries like for the gym, simply by matching the tags from the query with the tags in the database, and use that to generate a playlist or a radio station, right? Or you could also do things like querying the system with a song. And then given a seed song, what you could do is you could recommend other songs from the database that have similar tags, right? And use that to generate a playlist or a radio station. And so in some sense, that's kind of like what iTunes Genius does, but it's different here. What we're doing is we're basing ourselves entirely on the waveform, while iTunes Genius probably has some very different mechanisms that they use. Most likely, for example, collaborative filtering, what's in people's playlists and stuff like that, rather than analyzing the content of the song. Pandora has some type of music discovery functionality, but as many of you probably here know, the limitations that they have is that you have to kind of like seed the radio stations with artist names or song titles. And they're of course limited to the songs that they could manually index, which is a lot less than the number of songs, for example, on iTunes or on MySpace. One of the problems with Genius is that so it works well for fairly well-known music or known music that's listened to by a relative decent amount of people. But if you feed Genius, let's say, with some music that you just record in your own garage, then it's not going to give you any recommendations. In fact, I heard a story the other day that some very recent popular teenager music, when you would upload it to Genius, it would actually not be able to give you any recommendations because it's only been popular for like 2 weeks or things like that, and they didn't have enough usage. Was it you who told me?
Yeah.
Yeah, I didn't remember exactly.
Trumpet.
That's what it was?
Yeah. It's fixed now.
It took a couple of weeks.
Yeah.
So anyways, the thing here is that if you're building a system that can analyzes waveforms and indexes music based on the waveform, you can basically analyze any song for which you have the MP3 out there. And as I just talked about, you can kind of like deal with all kinds of queries, both queries driven by artist name or song title, but also like just natural language queries that don't involve any artist or song titles or seed songs, right? So anyways, that's kind of like the setup. What's interesting here with respect to VSU is that we actually did an anonymized playlist survey, I think it was about 2 years ago, based on one of our auto-tagging systems. And actually turns out if you anonymize the whole survey, that you get people vote in favor of Genius or playlists that we generated with equal probability, which is actually a very good result, because in some sense, like, you know, for songs that at least Genius can provide recommendations for, this is somehow like, you know, the best possible way of doing the recommendation, right? Because you know how songs co-appear in playlists, but being able to match that with an auto-tagging system was actually a very spectacular result. So there's certainly a lot of future to do that, trying to automatically annotate waveforms and build index databases for music recommendation based on that. And of course, what you can do as well, if you have it available, if the mood music is popular enough that you have a bunch of other information about this music available, like images about the artists or song lyrics or collaborative filtering information or videos or blogs or things like that. When you have that information available, you may also think about incorporating all that into your recommendation engine. I'm not really going to talk about that too much today, but that's also, you know, a possible direction to consider for music for which that extra information is available, for example, on MySpace and other sites like that. Okay, so that's kind of like the high-level picture here. Now, how do we build this black box, this auto tagger? Well, two main ingredients here are doing some signal processing and some machine learning. Basically, what we're doing at a high level, for starters, is we'll be collecting a bunch of examples of songs that characterize a certain tag, for example, rock songs. And then what we want to do is we want to basically train an algorithm that recognizes what is typical to the acoustic content of these rock songs, and then extrapolate that to new songs. So once the algorithm has discovered what are the typical acoustic patterns for these rock songs, if it then recognizes that pattern in a new song that it's never seen before, then it can decide that is actually a rock song based on recognizing that pattern. And so of course then the question is, like, how do we really do that internally? It's kind of like the first topic of this talk here. And so there's actually several different ways to do that, to build these models that recognize typical acoustic patterns in songs. There's generative approaches and discriminant approaches, etc., etc. I'm not going to spend too much time on discussing all these different types of approaches, but what I'll do is I'll give you an example of an approach here that we worked on, which is different from approaches that, for example, Doug worked on. By presenting that approach, what I'm going to try to do is not really like trying to say that this is the best possible approach or anything like that, but I think what's interesting here is the little exercise of seeing how an initial approach can possibly be improved to take into account, you know, temporal structure in music. I'm not going to go to temporal structure as in song-wide temporal structure, but at least trying to go beyond these 50 or 200 millisecond segments, which is what's most often known. So again, this is not the way to do it, but at least it's an example that will show you how we could possibly do a little bit more of longer-term temporal modeling. So what we're doing here is we're, first of all, as I say, collecting a set of example songs that is associated with a certain tag, for example, the rock tag, right? And what we're going to do here now is we're going to take a generative approach and we're going to estimate the distribution of the audio content for that tag, all right? So we're basically going to try to statistically model what the typical audio content is for songs that are associated with that tag through some distribution P. And the way we're going to do that is by taking at the song level. So let's look at this just at the song level for now. So let's say that you had to model the statistical distribution of the audio content of just one song. Well, the way this is usually done is you take the song, you chop the song into little pieces, little frames, which are usually, as I said, could be 50 milliseconds, 200 milliseconds, something like that. And then for each of these frames, you're going to extract a feature descriptor, right? The MMC chroma feature vectors, could be all kinds of stuff, but very often, you know, MFCCs and delta MFCCs are quite popular, basically spectral-based features. So for each of these frames, you extract the feature vector and you present them in some high-dimensional feature space. Okay, and so then the next thing you do is you basically model that cloud of feature vectors with some statistical model using expectation maximization or your other favorite algorithm. So now how do you do this for a tag? Well, you basically do the exact same thing. A tag is basically a collection of any songs associated with it. So for each of these songs, you extract the feature vectors, you throw them all together in one space, right? And then you fit the shape of that cloud with a statistical model by running EM, and as a result, you get the distribution of typical audio feature vectors for the tag block, right? It's as simple as that. There's some challenges with this here. Like for example, some challenges are that if you have a lot of songs associated with a tag, you can have a lot of data points here. So then the question is how to do this efficiently. I'll talk about this in a second. But basically, that's kind of like the approach. And then once you have these type of models for each tag in your vocabulary, then you can basically annotate a new unseen song by just taking the song, chop it into pieces, turn it into a feature cloud like that as well, and then just kind of like run this feature cloud by each of the models that you have available, and then just applying some simple Bayes rule allows you to come up with typical semantic annotations, some kind of like semantic histogram, right, of the annotations that characterize the song that your system had never seen before. Now back to the modeling. So, well, this is an example actually. I didn't know this was coming up, but this is just an example of such semantic annotation vector for, in this case, a Red Hot Chili Pepper song, where you can see that we can have vocabularies of 100, 200, even thousands of tags or more, organized in different categories, and then basically the height of each of these bars here indicates how likely a certain word is to be associated with that song as a result of that statistical analysis. Anyways, what I want to focus on is that distribution px that we're using to model the audio content for a given tag, so the song associated with the tag. And so, of course, the first kind of most simple model that we could use here is a Gaussian mixture model. And so basically, when we're modeling that feature cloud with a Gaussian mixture model, what we're basically doing is, as I said, we take the song, we chop it into pieces, but we're somehow throwing all these pieces, which are 20 to 80 to maybe 200 milliseconds in length, we're throwing them into a bag, kind of losing all the order information between these pieces, because all we're saying here is that we're going to model this cloud of feature vectors with a Gaussian mixture model. That's all we're doing in that case. But so from the perspective of this Gaussian mixture model, each of these samples is drawn independently and in no particular order from the Gaussian mixture model, which means that if we take all these frames here and we kind of mess up their order, then whatever you obtain in the end is still equally likely under the Gaussian mixture model, right? Because it doesn't really take the order of these frames into account. So how can we do something about this? So, well, a first step to trying to some temporal information into account could be to glue, let's say, 200 of these frames, 100 or 500, I mean something like that, but a good number of these frames, of consecutive frames, glue them together into sequences of 5 to 10 seconds, let's say. Okay, and that's what I've done down here. So I glue these together, and what I'm going to do then is I'm going to model the sequence of frames that I obtain here as a sample from a temporal model, more specifically a dynamic texture model, or basically a linear dynamic system. What is that type of model? Well, it's basically a model with a hidden layer and an observed layer. So this model has observation variables which basically characterize the instantaneous spectral characteristics of each of these frames here, but they're conditioned upon a hidden state variable x here, which evolves throughout time according to this linear equation here. So first thing to observe is that this hidden state variable x is a continuous variable. So we're not talking about discrete variables here like in HMMs. One of the reasons why we chose that is because HMMs are often used in speech recognition, where it makes sense to assume discrete states where each state is associated with a phoneme in the language. For music, it wasn't so clear to us that musical phonemes was a meaningful concept necessarily. I mean, this could be debated, but so in order to accommodate that, we chose for a model with a continuous hidden state here, leading us to a linear dynamic system where continuous hidden state evolves over time through this linear equation here, which basically models the temporal evolution of my observation variable y, which characterizes instantaneous spectral characteristics like timbre, and pitch, etc., etc. Okay, everybody gets that? So now there's one problem though, which is that if I would now draw the entire song on the slide here, and I would start drawing random like 5 to 10 second frames, 5 to 10 second sequences from that song, then it's not very likely that all of these sequences could be modeled with the same dynamic texture. The reason for that being is that songs are heterogeneous, right? There could be a guitar solo, an intro, an outro, a verse, a chorus, and it's not very likely that 5 to 10 second sequences from the guitar solo can be modeled with the same dynamic system than a 5 to 10 second sample from the intro, for example. So therefore what we're going to do is we're going to model songs with mixtures of these dynamic textures. So more specifically, let's say that, so we have a song here, down here, and what we have up here is a mixture of dynamic textures. So it's a mixture of these linear dynamic systems that is obtained as a model for the song. And basically the way to look at this is by realizing that every 5 to 10 second segment from my song is now basically a random draw from one of these 4 linear dynamic systems. So for example, in the intro, these 10-second sequences are draws from one of the dynamic systems that characterize my song. And then if you go further down into the song, like for example, there's a verse somewhere where the 10-second sequences are drawn from another linear dynamic system. If you go further down into the song, they're drawn from another mixture component. Right, so this is how we're modeling songs. So but still we're not modeling the songs with like 25 or 35 mixture components. So we're really trying to find some structure in the song where, for example, early on in the song you may have a verse that is modeled by the same dynamic system, then he's towards the end of the song or the next verse or something like that, right? Okay, so basically what we have here is a model of music that does look beyond 200 millisecond sequences or 200 millisecond frames and really looks at the dynamics within at least 5 to 10 seconds sequences. So of course now the question is, how do we estimate tag models? Well, we can do the same thing again. We can just look at all the songs that are associated with that tag in our training set, right? Then extract sequences from all these songs and throw them together in one big bag and model the bag with a tag model, right? It's basically the same thing, but now instead of extracting 200 millisecond segments from all these songs, you're going to be extracting 10-second sequences and model a collection of all these sequences with an overarching tag model, right? Which now in this case is also a dynamic texture mixture model. But the problem here is that in order to do the statistical estimation, if you have a lot of songs associated with the tag, it becomes very, very expensive to just run regular EM to fit this mixture of dynamic textures at the tag level. So what we're doing is we're going to do this in 2 stages. So first of all, we're just going to run standard EM for each of these songs to estimate mixture models for each of the songs. And then we're going to use an algorithm which is called, it's kind of like a hierarchical EM algorithm that will cluster all these mixture components, right, into a model that has fewer mixture components. Because of course one thing you can do is you can just take the union of all these song models, kind of like all aggregate them together, but then you end up with a mixture model with a lot of mixture components here. Like if you have 1,000 rock songs associated with the tag rock, you get 400 mixture components here, or 4,000. To do inference with that is just computationally very inefficient. So basically what we're doing is we're looking at all the mixture components we obtain here, and we're going to cluster them into the most meaningful ones where the mixture components in your resulting model could be different from any of the ones in here, so you could actually obtain novel cluster centers here, so to speak. The way this works mathematically is what we do is we draw virtual samples from all of these models, and then basically implement another EM step on top of that, but it turns out that because of the law of the large numbers, you can actually integrate out all the samples you draw from these models and efficiently estimate this higher level tag model from the parameters of all of these song level models. It's kind of like what happens under the hood. But the bottom line is, so this allows us to estimate tag models that do take into account temporal dynamics of music. I'm not going to go into too much more detail about this model here. Before I can show you a couple quick numbers on how these models perform, we have to talk a little bit about how I get my training data. How do I get my 1,000 examples of rock songs, for example? And so one of the first ways we got around this was about 5 years ago now, was by conducting a survey amongst undergraduate students in the music department, where basically it was kind of like a little mini Pandora. So we let them listen to a song, we gave them a big survey, and they annotated music with tags from all kinds of categories. So this was actually an interesting experiment to realize how much time and money it takes to collect even a small data set. But anyway, so we had a data set at that point, called it Cal 500, and so we had the first data set that we could evaluate our systems on. The way we evaluate it here, for example, this is just one metric that we're using, is by using single tag and then see which songs the automatic system ranks in the top 10 recommendation results, and look at how many of these recommendations are actually annotated with that tag in our Cal 500 dataset. Okay. And again, without giving you too many more details about how the experiments were exactly conducted, I mean, there's some cross-validation and all kind of things happening here. The only message I want to give away is basically this small table here, which doesn't mention a lot of other auto-tagger results and things like that, but which basically compares the models that we just looked at here, which is a GMM-based model, a DTM-based model, and then 2 other DTM-based models. The first thing to observe is that the performance, I mean, 1 is good, closer to 1 is better, closer to 0 is worse, so you can see that the performance actually does go up with roughly 10% by going from these GMM models that look at small frames to these dynamic texture models that look at 5 to 10 second sequences. What you notice here is these models are still dynamic texture mixtures, but they're trained in a different way. For example, this is the DTM model with the 4,000 mixture components by just aggregating everything after fitting the song models. And this is what is obtained by just running EM on all the songs together, so without doing this hierarchical EM type of estimation. And so what this tells us is that the fact that these numbers are lower, especially that this one here is lower, tells us that by running this hierarchical type of estimation procedure, you're actually regularizing the estimate as well in some way, and that's why your performance actually goes up or goes down if you go down the table here. So that's some kind of interesting results as well from a machine learning perspective, that not only for computational reasons is it a good idea to use this hierarchical estimation procedure, but also for regularization type purposes, it actually seems to be a good thing to do that. All right, any questions so far? It's my time.
You're okay, you have about 7 minutes.
Ah, cool. All right.
I was about to hold up the 5-minute thing.
All right, so basically, we see here that using temporal models really does make a difference, so that was certainly an interesting result. Now back to this Cal 500 data set and trying to, by the way, just for your information, this data set was collected like about 5 years ago, so nowadays there's been a lot of other efforts that have been done that go far beyond databases of only 500 songs. But anyways, what's nice about this data set here is that it's hardly annotated, so for every song we really have a clear indicator from the person who took the survey as whether a tag applies or not, which is valuable in certain ways. But still, it's very expensive to collect this, so what we did next to try to collect data at a slightly larger scale is we resorted to crowdsourcing or human computation to try to turn the time that people spend playing games into some useful data collection on the back end. So what we did is we designed this online music game that's incorporated into Facebook actually. And so the idea is that people kind of, go spend 5 or 10 minutes playing this game. This is mostly geared towards casual gamers. And so what happens in this game is that when people enter the game on Facebook, there's a song playing, which you should be hearing now because there's no speakers. We don't really hear much music, doesn't really matter. It makes it easier for me to explain it actually. So while the song is playing, there's a whole bunch of people that are playing the game at the same time. They're like in the same room at the same time, so to speak. And so they get like a little game that's presented to them in the middle of the screen that somehow tries to ask them some questions about the music. There's trivia rounds here that try to poll people for their knowledge about the music, which we don't really use, but we use it to entertain them a little bit. But the games that are important are the ones that are played right after a song starts playing, where, for example, a bunch of genres are shown to the people that are playing the game, and then they have to click on the genre they think is most appropriate. And then once the timer is up here, they can actually see what other people clicked on by seeing how these things grow. You see, like as these things grow, as other people have clicked on it, and then based on the agreement of the crowd, you actually gain more points if you agree with the majority of the people in the room there. So anyways, it turned out we implemented this game on Facebook, and in about, I think it was a matter of 3 to 6 months roughly, we had more than 8,000 registered players, about 150,000 of these game rounds played. And so this certainly allowed us to collect a good amount of tag data, but of course then the question is, how good is the quality of this type of data compared to doing like a survey in a controlled environment with students with a musical background, etc., right? So anyways, in order to evaluate that, what we did is we used that data to train our search engine, or better, to train our machine learning models, which we can then eventually use in the search engine. So more specifically, what we did is we used the data extracted from the Herded game to train our machine learning models, and we tested the predictions of our models on the Cal 500 dataset. Thanks. Okay. And we compared that to something that we thought was probably, a fairly viable alternative, which is we compared it to a model that was trained on Pandora data, which is data that was annotated by musical experts, right? Because the big question here is, can an online crowd of just casual players provide us with data that is as good as data provided by musical experts to train a musical audition system? That was kind of the question. Now, how did we get this data here? Well, Pandora data isn't really publicly available in any way, but it turns out that you can actually crawl some of their data from some of their web pages. This was an effort that was conducted entirely by Doug Turnbull while he was at Swarthmore. So we actually have this data set available as well for people who want to use it. It used to be called SWAT 10K, it's now called the Cal 10K data set. But so it is publicly available if you're interested in using it. So we use these two data sets to train two independent machine learning systems, and then tested both on our golden Cal 500 data. And as it turns out, over time, as more and more songs were analyzed by Herded, it turned out that the performance of machine learning systems trained from Herded went up and up and up over time. And in the end, we obtained a performance of about 96% of the performance of the expert trained system, which we consider as being pretty much confirming that we can extract useful data, or data that is as useful from just casual gamers and from musical experts. This band here is, so we actually did a couple experiments and then averaged out the results, so that's why we have error bars here, and these error bars are shaded until the point that this performance is no longer significantly different from the expert performance here based on some paired one-tailed t-test with p equal to 0.1 or something like that, I think it was. But so, one of the things that we started realizing while we were doing this was that if we're going to use data from the game to train a machine learning system, then we may as well use the machine learning system to feed data into the game and maybe present that data into the game that we believe is going to be the best data to improve the machine learning system faster, or what's known as active learning. So can we actively integrate the game and the machine learning system to kind of like make the machine learning system more intelligent quicker? And since I only have a few minutes left, I'm going to kind of jump through the details here, but the idea is pretty much, so I'm going to jump through this. So what we had to do here is we had to somehow figure out as to which song should we feed next into the game, which song should we analyze next in order to update our machine learning models more effectively in the next round of model updates. Right? And so we came up with an approach which is actually fairly simple as a first step approach, but it isn't an approach that uses the current models to suggest the next songs to be fed into the game. And if you do that, if you engage in an active learning loop like that, then it actually turns out that the performance of the herded-based, the data extracted from the performance from that can be obtained by training machine learning models on the data that was extracted from herded so far in time actually goes up quicker. In fact, it reaches this 96 performance in about half of the time of doing some random sampling strategy. It also reaches this statistically significant point in about half the time or half the number of analyzed songs as when you just do a random sampling strategy. So basically what this tells us is that doing some kind of active learning like that really allows us to extract useful data from casual gamers more efficiently and with less human effort than if you just do some kind of random feeding of data into the game. Couple more things here. So everything following from here is stuff that we haven't really done yet. So this is just kind of future music. So one thing that is interesting by embedding this game into Pandora is that they actually provide you with demographic information. So as a result of that, we can actually start analyzing whether there's any difference between mellow rock as judged by a person from one demographic category versus another demographic category. And so you can actually start personalizing some of these annotation models. So that's one thing. And the other thing that I think is kind of interesting as well here is basically how do we bring the recommendations to people now. And so one of the routes we're trying to pursue here is called zero-click recommendation, which is basically instead of requiring a person to actively provide queries as to what they're doing or what they're feeling like in order to construct playlists, can we actually use the sensors in a smartphone to automatically detect what a person is doing or how they're feeling, and then provide recommendations based on that. So basically, your phone is in your pocket, there is a headset connected to it, and you're kind of like listening to music that changes depending on what your phone thinks that you're doing or feeling like. And so you may think that this sounds a little bit futuristic, but the thing is that, in some sense, all these, the signals from the sensors in a phone, at least accelerometer signals, for example, are just one-dimensional signals, so you can kind of try to analyze them with similar techniques as the ones you would use to analyze music with, right? I think, having worked on music, we have a competitive advantage to try to, build something like that. So anyway, so let's say if the system detects the person is running, then play some energetic music. If they're just mellowing out late at night, then play some mellower type music. So anyway, so that kind of like completes my talk, as in like write music. How do we figure out what romantic music or jazz music is? Bring it to the right people. Can we personalize music search and recommendation, and also can we automatically kind of provide these recommendations at the right time in the right place? Right, to kind of provide music to people in different circumstances from this very extensive pool of possibilities that's out there. I certainly have to extensively thank a lot of PhD students, master students, and undergraduate students that work with me on this, and extensive funding from all kinds of sources. With a very central mention here of the organizers of this workshop. Thank you very much.